largest telescope ever flown launched into deep space.
There's going to be a lot more discoveries to come.
In the expansive realm of the cosmos, where enigmas of the universe have remained concealed for countless ages, a remarkable instrument stands ready to push the frontiers of our comprehension. The James Webb Space Telescope, an extraordinary testament to human innovation, holds the potential to fundamentally redefine our perception of the cosmos. Equipped with advanced instruments and cutting-edge technology, this spaceborne observatory is poised to revolutionize our data-gathering capabilities of remote celestial bodies, unravel the enigmas of extraterrestrial city lights, and question the very underpinnings of our comprehension of the universe. So join us on a captivating journey through the cosmos as we delve into the incredible photos, discoveries, and data from the James Webb Space Telescope that will transform our understanding of the universe. JWST's quest for extraterrestrial city lights. The JWST is undoubtedly the most powerful space telescope in existence. Designed for infrared astronomy, it can peer deep into space and see things that are very faint, old, and that are extremely far away. It can see things which other massive telescopes before it cannot. The JWST was born from a big collaboration between NASA, the European Space Agency, and the Canadian Space Agency. Our planet's biggest telescope yet has a giant 6.5-meter mirror made of gold-plated beryllium, much bigger than Hubble's, allowing it to collect a lot lighter. It equally observes in the infrared range, which is different from Hubble. To do this, it has to be super cold, colder than minus 223 degrees Celsius, so it doesn't interfere with the light it's trying to capture. Webb presently sits about 1.5 million kilometers from Earth, near the Sun-Earth L2 point, where a sun shield protects it from getting too warm. You see, this gigantic telescope took a very long time to build and cost a lot, about $10 billion in all. But since its launch on December 25, 2020, and subsequent commissioning, the JWST has been found to be worth every penny. It's gone on to make several groundbreaking and unprecedented discoveries, unraveling many unknown and amazing things about outer space. For context, with the help of the JWST, astronomers are now confident that we might just be on the verge of uncovering the presence of alien cities on distant planets through their emitted light. Instead of solely relying on the detection of radio signals, scientists are now exploring the idea of using the illumination from city lights on exoplanets as a potential indicator of extraterrestrial civilizations. Equipped with the advanced sensors on any telescope in the universe, the JWST now stands ready to peer into the vast cosmic expanse and unravel even more astonishing discoveries, exploring Roe Ophiuchus with NASA's Webb telescope. NASA celebrated the first year of James Webb Space Telescope observations with an image known as Roe Ophiuchus. This captivating picture showcases the Ophiuchus star-forming region, which is remarkably close to Earth, lying within a mere 400 light-years distance. It stands as Earth's nearest star-forming region. Contrasting with its more renowned counterparts, such as those captured by the Hubble Space Telescope, Roe Ophiuchus represents a relatively small star-forming area. Here, a single star, comparable in size to our Sun or even larger, dominates the lower left portion of the image. The remaining stars are smaller and likely to evolve into red dwarfs over time. The use of infrared technology enables us to peer through the veil of gas and dust, unveiling the stars concealed within. What's particularly enchanting about Roe Ophiuchus is that it's an object you can capture with a modest telescope or even a digital camera mounted on a sturdy tripod. Especially during the summer months when the Milky Way graces the night sky overhead, you can immortalize this breathtaking region in your photographs. It's a truly iconic feature within our Milky Way galaxy. The evolution of deep-field astronomy. Studying the distant corners of the universe to unravel the origins of the first galaxies is a primary scientific objective of the James Webb Space Telescope, JWST. This pursuit is made feasible by the remarkable fact that light takes billions of years to traverse the expanse of our cosmos. The telescope peers into the past, capturing the light emitted by celestial objects billions of years ago. Astronomers employ light years as their unit of measurement, denoting the maximum distance light can journey in a single year. The team's initial graphic underscored this fundamental reality. On July 11, 2022, U.S. President Joe Biden unveiled an extraordinary deep-field photograph while addressing the nation from the White House. This image was taken by the JWST, harkening back to a concept first explored by the Hubble Space Telescope when it diligently scrutinized a minuscule section of the heavens for an uninterrupted span of 10 days, commencing on December 18, 1995. These deep fields have become renowned for their ability to focus on seemingly infinitesimal regions of the sky, each comprising a mere fraction of a percent of the entire celestial canvas. Astonishingly, within these minute sections, the Hubble telescope discovered approximately 3,000 previously unknown entities, the majority of which were galaxies situated at distances spanning billions of light-years from our vantage point. The evolution of galaxies through JWST's lens. A similarly small portion of the sky is observed by the JWST's deep field, with its focus centered on the galaxy cluster known as SMACS 0723. This particular galaxy, SMACS 0723, is astonishingly distant, located a staggering 4.6 billion light-years away. What makes this observation particularly intriguing is the profound effect of its powerful gravitational field on the galaxies situated even farther behind it. These background galaxies undergo significant distortion, often taking on the form of expansive arcs, where the gravitational pull is most intense. In a remarkable instance, it was calculated that light from a distant galaxy took a staggering 13.1 billion years to traverse the vastness of space and reach the JWST's telescope. This phenomenon occurs because, over time, the light emitted by these galaxies undergoes a stretching effect as the universe itself expands. Due to their extreme distance, the primary target galaxies observed by the JWST have had their visible light, originating from their stars, stretched into the infrared spectrum. Astronomers are now poised to make direct comparisons between the observations captured by the JWST and the visible light images of nearby galaxies obtained by telescopes like Hubble and others. Gathering data at these specific wavelengths will provide crucial insights into the evolution of galaxies throughout cosmic history, shedding light on how they have evolved and coalesced into the complex structures we see in the universe today. The JWST's initial deep-field image was not only with its multitude of galaxies, but also with the speed at which it was taken, mere hours instead of days. Wherever it looks, it inevitably encounters galaxies. The only objects serving as natural magnifying glasses are galaxy clusters. Scientists employ the JWST to photograph a pair of galaxies known as 55191. This enables them to investigate how the light from one galaxy changes as it passes through the other. The findings from this research will unveil details about the dust within the intervening galaxy. A close-up of Stefans Quintet's celestial ballet. Galaxies and black holes were a subject of interest when the telescope captured its initial photos. Among these, there was a close-knit group known as Stefans Quintet, containing 4 galaxies engaged in a gravitational dance due to their proximity. The 5th galaxy in this assembly appears to be nearby, but in reality it's much closer to us and coincidentally lines up with the others in our line of sight. Together, these 4 interacting galaxies create a unique laboratory for astronomers to explore how galaxies interact and eventually merge. Such mergers were likely common in the early universe, playing a significant role in the formation of the vast galactic structures we observe today. They are also thought to be linked to the growth of supermassive black holes, each residing at the center of a galaxy. The JWST observed Stefans Quintet using its NIRCam and MIRI sensors, with MIRI's images in particular surprising astronomers because they revealed unexpected forms of the galaxies. Unveiling the phantom Galaxy M74. A remarkable achievement of the MIRI instrument involves the study of the phantom Galaxy M74. This spiral galaxy is situated 32 million light-years away from Earth and is nearly face-on to us. The striking spiral arms, which define spiral galaxies, have always intrigued astronomers. However, until now, no one has observed them so clearly. For the first time, we can see the spiral arms of this galaxy, where stars are actively forming, extending down into the galaxy's core. Collaborations are crucial as we aim to combine the new observations from the telescope with data from existing observatories. This collaboration will deepen our understanding of the celestial objects under examination and hopefully lead to exciting discoveries. One of the key advantages of infrared astronomy, which the JWST specializes in, is its ability to peer deep into star-forming regions. This is because longer wavelengths, like those in the infrared spectrum, are less affected by dust, molecules, and atoms, making the very objects that obscure our view of star nurseries almost transparent. This capability allows us to explore the life cycle of stars with greater clarity. Another image captured by the JWST brought us closer to CAM's observation of the star-forming region NGC 3324, located about 7,500 light-years away in the Carina Nebula. The Carina Nebula, although composed mainly of gas and dust shaped by the illumination of stars, presents a breathtaking vista resembling a landscape. What's truly astonishing is the ability to use infrared technology to peer into this once-hidden realm, now revealed in all its magnificent glory. Initially dubbed the cosmic cliffs upon its discovery, this vast expanse of gaseous cliffs resembled a mountain range. In reality, it marked the boundary of a massive cavity slowly eroded by the intense ultraviolet radiation emanating from young stars, a stellar nursery in a distant galaxy. This has to be one of the best pictures of the year. It captures the Tarantula Nebula, which is among the largest known star-forming regions ever spotted by astronomers. Situated in the Large Magellanic Cloud, a galaxy located hundreds of thousands of light-years away from our own Milky Way, it's an entirely different celestial neighborhood. Despite its distant location, the Tarantula Nebula stands out due to its immense size and the sheer number of stars being born within it. Many of these emerging stars surpass the mass of our own Sun by several times. A recurring point worth mentioning is that the JWST is equipped with an array of infrared instruments. Infrared light has the remarkable property of allowing us to peer through the typically obscuring effects of gas and dust that shroud areas like star-forming regions. While the Hubble Space Telescope might reveal such regions as hazy patches, the James Webb Telescope can pierce through this dust and unveil the actual process of star formation occurring within these nebulous cocoons. In this particular image of the Tarantula Nebula, you can discern various knots and zones where new stars are taking shape. The infrared capability enables us to see through the surrounding gas and dust, offering glimpses of protostars emitting radiation that pushes away the nebular material, gradually unveiling these nascent stars. Over time, these colossal dust-filled cavities will expand, progressively exposing all the stars being born within. Remarkably, this picture is available in high resolution, boasting an impressive 14,000 by 8,000 pixels. Although it was among the first images captured by the JWST, astronomers initially chose to release the image of the Carina Nebula first, holding on to this Tarantula Nebula gem for a later unveiling. Unveiling the secrets of the Orion Nebula with JWST. The Tarantula Nebula stands out as one of the most prominent regions in the universe where new stars are being born. On the other hand, the Orion Nebula holds a special place as perhaps the most well-known star-forming region, likely due to its fame. This made it a natural choice for astronomers to direct the telescope. The Orion Nebula is a recognizable sight for those blessed with clear, dark skies. Even with the naked eye, you can spot it in the night sky. If you have binoculars or a small telescope, the view becomes even more captivating. The specific region we are looking at here is known as the Orion bar. When we compare the image captured by Webb with the one taken by the Hubble Space Telescope, we notice a remarkable difference. Pay close attention to the bright stars and how precisely they are aligned. This comparison vividly illustrates the superior optical capabilities of the JWST compared to the Hubble. While both telescopes reveal the major structures, the JWST provides a sharper and clearer image, thanks to its impressive 6.5-meter mirror, dwarfing the Hubble's 2.5-meter mirror. One of the most intriguing pictures from this year features a Wolf-Rayet star, WR140. These stars are newly formed and incredibly hot, emitting vast amounts of radiation. When astronomers first examined an image of this star, they noticed something truly unusual: concentric rings encircling it. Remarkably, this is not an artifact or distortion in the image. These rings are very much real. They exist in the surrounding nebula material of the star. Here's what's happening. The star has a companion in a binary system. The star ejects material into the surrounding cloud or nebula. As the stellar companion moves through this material, it carves out rings, one after the other. It's somewhat akin to counting tree rings to determine a tree's age. In this case, each ring corresponds to approximately 8 years of the star's evolution. What makes it even more fascinating is that this binary companion orbits the star every 8 years, so each ring serves as a record of 8 years' worth of changes in this young star's life cycle. The Pillars of Creation through Hubble's lens. One of the most famous images captured by the Hubble Space Telescope is undoubtedly the Pillars of Creation. This breathtaking image showcases another region where stars are actively forming, specifically within the Eagle Nebula. Interestingly, you can observe the Eagle Nebula with a small telescope, and if you attach a camera, you can even capture images of the Pillars of Creation, although not as spectacular as the Hubble's. Earlier, we mentioned the Tarantula Nebula and how stars within these regions generate incredibly powerful stellar winds. These winds play a crucial role in shaping the surrounding nebula's structure. In the case of the Pillars of Creation, imagine the top portion as a nascent star enclosed by a shroud of gas and dust. However, the combined force of all the other stars in the nebula acts like a powerful wind, essentially eroding and sculpting the material. This results in the formation of what appears to be a comet-like tail or column extending away from the star. Astronomers believe that these pillars, as we currently perceive them, have likely already collapsed due to the influence of these intense stellar winds. Nonetheless, it will take several thousand years before we witness a new incarnation of this phenomenon. The original Hubble image offered a stunning view of this process, but then along came the James Webb Space Telescope, providing an even higher resolution picture. What's more, it can penetrate through some of the gas and dust that obscured the Hubble's view, granting us not only greater detail but also something akin to X-ray vision, allowing us to peer into these regions where stars are actively being born. From red giants to white dwarfs. In the latter stages of a star's life, the JWST has shed light on how stars go through their life cycles. Sun-like stars, for instance, undergo a transformation where they expand into red giants before eventually contracting into white dwarfs, essentially becoming stellar remnants. During this contraction, they shed their outer layers, forming what's known as a planetary nebula, although this name doesn't quite capture the phenomenon accurately. The JWST's image of the Southern Ring Nebula vividly illustrates this captivating process. The star goes through a repeated cycle of expelling layers of matter from its outer shell over thousands of years as it transitions into a white dwarf. The remaining core of the star then begins to compress and heat up, initiating a new phase of energy generation and pulsations. Each pulsation results in the ejection of another layer of material. This cycle continues indefinitely until there is simply not enough material left to sustain the core's pressure and trigger nuclear fusion. At this point, the star becomes a white dwarf. Interestingly, this is the same fate that awaits our own sun in approximately 4.5 billion years. James Webb's quest for exoplanetary secrets. One of the primary tasks of the James Webb Space Telescope is to observe planets in various stages of development, from newly forming ones to more mature planets orbiting distant stars. The telescope's unique infrared capabilities enable it to peer through the veils of gas and dust surrounding star-forming regions, allowing us to witness the birth of planets around newly emerging stars. This capability also permits scientists to analyze the chemical compositions of a planet's atmosphere separately from the chemicals found in the star it orbits. To achieve this, astronomers carefully point the JWST at a star where they anticipate a planetary transit, meaning the planet will pass directly in front of the star from our vantage point. The telescope captures images of both the star and the planet as the planet crosses in front of it. This transit reveals the composition of the planet's atmosphere. For instance, in the case of WASP-39b, a planet located approximately 700 light-years away, the JWST successfully detected the presence of carbon dioxide in its atmosphere. This groundbreaking observation marked the first time carbon dioxide had been identified on another planet. Additionally, the JWST detected other substances like water vapor, potassium, sodium, and carbon monoxide in the planet's atmosphere, many of which had never before been observed in the atmospheres of exoplanets. The TRAPPIST-1 system is generating a lot of anticipation among space enthusiasts. TRAPPIST-1, a red dwarf star, has 7 Earth-sized planets orbiting around it. What's particularly intriguing is that some of these planets are positioned within the habitable zone, where conditions for life could potentially exist. If we were to pinpoint a place with the highest likelihood of harboring life beyond Earth, this system would be a strong contender. The telescope is methodically studying these planets, scrutinizing their atmospheres, or in some cases, the absence of atmospheres. In its inaugural year, Webb has managed to analyze only 2 of these planets. The first, TRAPPIST-1b, resembles a supermercury, and as expected, it lacks an atmosphere. However, the second planet, TRAPPIST-1c, has piqued astronomers' interest. They had high hopes for this planet, hoping it might resemble a super-Venus. Unfortunately, like its counterpart, it also lacks an atmosphere. So, as it stands, we have 2 rocky, airless worlds in orbit around TRAPPIST-1, but there are still 5 more to investigate. Now it's time for today's subscriber pick. It's time for today's topic. Can we identify alien cities on distant planets by observing their emitted light? A groundbreaking study suggests that such a possibility exists. Instead of relying solely on detecting radio signals, scientists are now exploring the idea of using city lights illumination on exoplanets as a potential indicator of extraterrestrial civilizations. Equipped with advanced sensors, the James Webb Space Telescope is poised to examine the vast cosmic expanse. Could it capture the faint glow of artificial illumination, an unmistakable sign of intelligent beings beyond Earth? The potential implications of this concept are truly remarkable. Consider the idea that hidden within the data collected by the Webb telescope, we may find compelling evidence of thriving alien cities. What if the mere detection of their urban landscapes could confirm the existence of advanced societies? It's crucial to emphasize that this pursuit is not a product of science fiction. It represents a legitimate and rigorous scientific endeavor. The quest for techno-signatures is gaining significant momentum, and our effort to explore cosmic neighbors has never been more exciting. It appears that the cosmos may contain more than just celestial bodies like stars and planets. Kindly share your insights regarding this matter. Class 0 Protostars with James Webb Telescope. James Webb is equipped with various instruments specialized for different tasks. In the first picture, we used the near-infrared astronomy camera, known as NIRCam. In the second picture, we employed the mid-infrared instrument, or Miriam, which operates at a different wavelength of infrared light. Miriam allows us to observe the gas and dust surrounding stars, but it tends to obscure the stars themselves. They don't appear as bright in this mid-infrared view. Using different wavelengths of light with Webb helps us uncover various aspects of the nebula. Astronomers can leverage this capability to gain deeper insights into the star-forming region. James Webb has recently focused on newly forming stars that aren't surrounded by clouds of gas and dust. In this specific case, you're looking at a protostar classified as a Class 0 protostar. This means the star is only around 100,000 years old and is located approximately 430 light-years away from Earth. This star is encircled by an accretion disk, a disk of material being drawn into the star to increase its size. This is where we anticipate the formation of planets around the star. Additionally, magnetic field lines are ejecting material along the star's poles, propelling it into space. If you could travel back in time and observe the Sun during its formation in the solar nebula, this is akin to what you might witness within a few 100,000 years after the birth of the solar system. James Webb has captured numerous galaxies in its observations. These images are instantly recognizable, often characterized by dark purples and salmon colors. This aesthetic has earned it the moniker of the eldritch horror version of astrophotography. The colors in these images primarily highlight areas rich in gas and dust, rather than the brighter, older stars. They provide a unique view of the regions where stars are currently forming, often within the galactic arms of their respective galaxies. Thus, the images from James Webb effectively reveal the locations of these arms and where future star-forming regions are likely to emerge, akin to revealing the underlying structure of a galaxy. Gravitational lensing superpower. The James Webb Space Telescope is not only powerful on its own, but becomes exceptionally potent when it aligns with a gravitational lens. This extraordinary setup harnesses the gravitational force of an entire cluster of galaxies to act as a natural lens, allowing for significantly more precise observations of objects situated beyond this lens. These observations reveal details about the elements present in these remote galaxies that would be otherwise invisible using the telescope's inherent capabilities. Moreover, this configuration offers additional advantages. In one notable instance, James Webb detected multiple occurrences of the same supernova event within a galaxy. This phenomenon arises because the light from the supernova follows distinct paths around the gravitational lens created by the galaxy cluster. As a result, astronomers observed the same Type 1a supernova event happening multiple times, contingent on the different routes the light took around the intervening galaxy. The sheer potential of using the gravitational pull of a galaxy cluster as a natural telescope is truly remarkable. It enables us to observe objects with tens of thousands of times greater clarity, compared to relying solely on the telescope's capabilities. While we continue to grapple with the mystery of dark matter, we can, astonishingly, utilize it as a tool for scientific discovery. Unveiling cosmic collisions and starlight brilliance. This picture will appear instantly recognizable as a James Webb image. You can easily spot the distinctive six-sided star shape, which is a result of the hexagonal mirrors. These mirrors are responsible for creating this unique star pattern when capturing bright objects with the Webb telescope. If you examine the image closely, you'll notice two additional lines stemming from the struts that support James Webb's secondary mirror. In this particular image, we're looking at an astronomical object known as ARP-220, which results from the collision of two galaxies. This collision generates an exceptionally intense brightness, to the point where it's beginning to overwhelm the sensors on the telescope. In visible light, this image shows the fascinating merger of two galaxies, which is quite captivating. However, when viewed in the infrared spectrum, it shines with the radiance of 1 trillion suns, approximately 100 times brighter than the Milky Way. This marks the initial stage of the gradual transformation of these colossal galaxies. Eventually, they will evolve into massive elliptical galaxies similar to M87. These giants are the outcome of numerous galactic collisions over time, as they assimilate smaller dwarf galaxies within their vicinity. Once they've absorbed all available smaller galaxies, they settle into a state where they predominantly consist of a multitude of stars, gradually transitioning into redder and redder stars as time passes. The enigmatic supermassive black hole of JWST. The JWST telescope is doing a cool survey called JADES. It's like a high-tech version of Hubble's famous deep field, but it looks at a specific part of the sky. They spend a lot of time studying this area, and they're going to do even more. What's amazing is that JWST already shows us 10 times more galaxies and gives us 15 times more detail than Hubble. They use something called spectroscopy, where they break up the light from faraway stuff into colors like a rainbow and look at special lines to figure out what things in space are made of. They found organic stuff in a far-off galaxy that's old. It's like the stuff left behind from a chimney fire. And it's a big deal because it's from way back when the universe was just starting. This is exciting because these organic bits are what life might come from, and they could help us understand how life on Earth began. JWST isn't just looking at galaxies, it's also spotting supermassive black holes called quasars. They're like giant vacuum cleaners in space that eat everything and shine super bright. JWST saw one called Sears 1019, which was only 9 million times heavier than our Sun, and it was around when the universe was still pretty young. This surprises scientists because they thought these black holes couldn't grow that fast back then. If we look at the universe as a whole, it's like a giant spider web with galaxies and clusters of galaxies connected by long strings and empty spaces in between. JWST is helping us see back to when this web was just starting to form. They saw a big galaxy acting like a magnet, pulling in smaller ones to make a long string of galaxies that stretched for 3 million light-years. This happened when the universe was only 830 million years old, so it gives us a peek at how things were back then. How James Webb overcame a cosmic collision. It has been an exciting year of scientific observations for the James Webb Space Telescope, but there were some challenges along the way. The first major issue encountered was the impact of micrometeorites. This was expected since tiny dust particles are present throughout the solar system. It was anticipated that these particles might collide with Webb's mirror, gradually degrading its optical capabilities. However, in May, a relatively large piece of dust collided with the telescope, causing noticeable damage. Nevertheless, Webb's capabilities still exceed the expectations of astronomers. Despite the damage, the telescope remains highly functional. In response to this incident, the team working with James Webb decided to adjust the telescope's orbit strategy. Previously, it could turn in any direction to observe various targets. However, based on this experience, they opted to conduct most observations downstream, following the telescope's orbit. This minimizes the risk of collisions with dust particles, as they will now only hit the telescope if they catch up to its orbit. This results in lower collision velocities and less damage to the optics. Additionally, Webb faced an issue with its MIRI instrument, specifically the medium-resolution spectroscopy mode. Engineers detected excessive friction in this mode, prompting them to temporarily deactivate it. They continued to use the other modes while diagnosing the problem. After identifying the issue, they successfully restored the MIRI instrument to full functionality. During this period, astronomers were still able to utilize the other modes of the MIRI instrument for their observations. Which aspect of the James Webb Space Telescope's mission did you find the most fascinating? Let us know in the comments.